Dr. Apurba Laha is currently a professor at the Department of Electrical Engineering, IIT Bombay, India. After his PhD from the Indian Institute of Science, Bangalore in 2004, he moved to Germany as an Alexander von Humboldt postdoctoral research fellow at Leibniz University, Hanover. He was later offered a senior scientist position at the same university in 2007, and 2 years later, he became the group leader to lead a research group on functional oxides and semiconductor thin films and nanostructures. In 2009, Dr. Laha was nominated among the best 3 researchers from Leibniz University, Hanover, for Heinz-Meyer-Leibniz Prize awarded by the German Research Foundation. At IIT Bombay, Dr. Laha leads a research group working on the epitaxial growth of gallium nitride, aluminum nitride, indium nitride, and their alloys, heterostructures, using a plasma-assisted molecular epitaxy technique. His group also focuses on the design and fabrication of various III-Nitride electronic and optoelectronic devices, such as high electron mobility transistors, light-emitting diodes, laser diodes, and photodetectors. Dr. Laha has published 120 articles in international journals and conference proceedings and delivered more than 60 invited talks. On behalf of all the members of RIOS, I welcome you, sir, to this webinar. And I also welcome all the invited guests and participants to the webinar. Now, a humble request to all the participants. All are requested to keep your microphones muted till the end of the webinar. After the talk, time will be given for interaction with the speaker. Also, all of you please take care not to present your screen in between. Link for generating e-certificates and providing feedback will be given at the end of the webinar. Now, I kindly request Professor Apurba Laha to begin the presentation.
Welcome to this seminar and greetings from IIT Bombay, Mumbai, and good evening to all of you for your time. And I hope at the end of the presentations, I'll be able to communicate some of the things that we are doing. And I'm also looking for some of the collaborators, students, and postdocs, for examples, and to work with me in future. So the presentation is primarily about the III-Nitride structures. So the reason I put it like III-Nitride rather than the compound or 3-5 semiconductor, because typically by 3-5 semiconductor, we understand gallium arsenide, and III-Nitride material behave very differently, although they are typically group 3 and group 5 the elements. However, I prefer to call them III-Nitride because of their distinguished properties. Now, before I begin my presentations, I would like to take this opportunity to introduce some of the activities that we do as a group in IIT Bombay. So my group focuses on primarily 3 areas in the III-Nitride optoelectronic devices. One of the major sort of work that we do is the high electron mobility transistors based on gallium nitride, aluminum gallium nitride based heterostructures. And then another major activity that we work on, the green laser or green LEDs, which focuses on making the light emitting source, particularly in the range of 530 or 500 nanometers. The another one, I am also working on the UV LEDs based on the nanowire or aluminum gallium nitrides or III-Nitride nanowire. And the another very exciting, primarily research sort of dominated work, which our group focuses on, is that single photon source based on the III-Nitride material. So particularly the single photon source, we are looking for the sources that would be able to, that will sort of emit a single photon or one photon at a time at room temperature. That's our final goal, and that's our wish. And I'm going to show at the end of my presentations to what extent we could progress in these directions. Okay, so with that, I just try to sort of summarize what I'm going to present. You see, the primary or the major challenges of this III-Nitride or gallium nitride based materials is the growth. There are several reasons for it. I'm going to explain, and you will see at the during the presentations, and I mean how we try to circumvent those challenges and eventually come out with a certain set of structures useful for a certain device. Okay, so I start with the heterostructure. So heterostructure means like it's a planar layer. two-dimensional layers with the multiple stacks of different compositions, all are around 3 nitrides. So that means the aluminum, gallium nitride, sometime indium, aluminum, gallium nitrides. Now, and I will also spend significant amount of time to show you how we grow these materials with the help of the state-of-the-art molecular beam epitaxy. Usually, there are two well-known techniques or used techniques for growing the 3-nitride materials. One is this MOCVD. So MOCVD has many more advantages while you are growing the 3-nitride material. Particularly, those are useful for the electronic devices such as the high electron mobility transistors, because the MOCVD has much higher throughput, and also the growth rate is much higher, so we can produce a very large number of devices in much shorter time. MBE, being in a research-based tool, has a lot more advantages to understand what goes on at the time of growth. It's very early stage, for examples, because the MBE can afford to have some of the tools that eventually help us to understand the layer configurations as well as the growth. So I'm going to talk about that and how we kind of sort of play with those advantages or those parameters to come up with the different structures. So one of the things or major activities that our group sort of deal with nowadays is to look at the nanowire-based devices. So this nanowire-based devices is, you will see here, so we talk about the LEDs, we talk about the emitters, for example, single photon source as well. So mostly all around the nanowire. So I'm going to show you how the nanowire eventually circumvent the problem that are associated with the two-dimensional heterostructures of 3-nitride materials. And then the different devices on the way I'm going to show you, and their advantages, their behaviors, and then how are basically linked to the structural changes that we are talking about. And then I will also show about the some of the recent results, and also at the end I'm going to end with showing some of the activities related to the single photon source that are operating at room temperatures, for example. Okay, so with that I'm going to just start here. So as I said, the most of the growth or all the growth that we do here are done or carried out in plasma assisted molecular beam epitaxy systems. So this is our bread and butter. So that's every day we are using this one. Now, one of the advantages of this MBE or molecular beam epitaxy, particularly the plasma assisted molecular beam epitaxy, is that we could create, or we can create, a different structure. As you see on the right side, first one is the planar, then the nanowire, then the quantum wire, quantum dot, and heterostructure multi-quantum well. So in all cases, all we have to play with the process parameter. We do not need any sort of catalyst to grow the nanowire, unlike you require in a CVD system. So that's the great advantage of the molecular beam epitaxy systems. Now, molecular beam epitaxy system comes with the two different configurations. One is looking is to, for example, the nitrogen source is the primary concern in MBE systems. Unlike the gallium arsenides, you have gallium and arsenic, both sources. But here, the getting a nitrogen, activated nitrogen source is a bigger concern. So the two ways to get it, one is the plasma, the other is the ammonia. So the ammonia-based MBE are also quite popular when we're looking at the gallium nitride-based the electronic devices particularly. However, there are the logistical limitations with the ammonia-based MBE. You have a safety concern. The plasma-assisted molecular beam epitaxy or the plasma source of nitrogen, it's a relatively newer discovery. However, it is now, if we can hit the proper process parameters, you can sort of compare the device as good as the MOCVD grown and plus the ammonia grown MBE layer, for example. So here at IIT Bombay, we primarily deal with or working with the plasma assisted molecular beam epitaxy. Okay, now, as I said, unlike the MOCVD, MBE can afford to have some of the tools that will help us to understand the growth. So one of the things that we have, or one of the tools that we have, which we call the eye of our MB system, is called the REID, which is the reflection high energy electron diffraction techniques. Now, so because it's work in a reflection mode, which is the specular beam as well as the diffractions, so we can know at the time of growth whether you are growing a planar layer, whether you are growing, for example, say a 3D structure, for example. This is an example which you see on the left is a streak, which is a symbol of, which is a signature of a two-dimensional growth. If you have a two-dimensional crystals with a very ordered structures, you would expect some sort of a streaky behavior on the read. So that is at the real-time growth. So you know that whether your layer are single crystallines or there is a deviation from single crystalline two-dimensional layer. That is something that you're growing. On the other hand, when you're looking at the different structure that I will show during my presentations, you may actually see some of the spotty features. This 3D spotty features actually, or the spot, for example, is a signature of 3D structures. So how we optimize the structures by looking at the read is that something I'm going to show, and it's very helpful to come up with a certain heterostructures. So it's very useful, and it's always that we try to exploit the facility and try to exploit the signature that you get from the read image. All right, now coming to III-Nitride semiconductors, or gallium nitride to be typically, which is the well-known to all. So you know that the solid-state lighting particularly has revolutionized the way we light the world. And it has happened during the last couple of decades. And it was not a easy journey or a smooth journey when it started, since it started. It eventually went through a lot of struggle at the beginning, but it was primarily because of the challenge to grow the good quality heterostructure that is required for a certain device, for example. Now, if you want to grow a crystals, particularly, for example, the layer or on a substrate, so what you need is a substrate, right? And so when you grow a layer in a single crystal form or an epitaxial form, so you look for the structures. The first thing you need to know is what structures your material has. And then you look for a suitable substrate that would support to grow these kind of structures. So let's look at what the gallium nitride structure. Gallium nitride, if you take a unit cell of gallium nitride, and it shows like hexagonal woodside structures where the alternate layers are gallium and nitrogens. Now, interesting thing about this structure is that because the gallium and nitrogens has a two different electronegativity, so the structure itself is an unique in its property because it inherently has a polarizations or an electric field built into the crystals itself. So that electric field sometimes helps us to create a unique device that I'm going to show, but sometimes it's creates some sort of obstacles or limitations when you're looking at the devices, particularly optoelectronic devices or the light emission from the structures, for example. So the another interesting or unique properties of gallium nitride or III-Nitride material is that, it has a band gap, or if you sort of mix the three different elements, which I'm talking about, indium, gallium, and aluminum with the nitrogens. So you can cover the entire visible spectrum, and all the way you can reach up to deep UV as high as 250, 220 nanometer, for example. Now that is given by the figure on the left, you can see here. So if you take considerations of aluminum nitride, which is group 3 aluminum and nitrogens, and then aluminum nitride has a band gap of 6.2 electron volt. That would eventually give you the light in the wavelength of 210 nanometers, for example. So in between comes gallium nitrides, which is 365 nanometer if you consider the band gap, and then the indium nitride, which gives you a band the light in somewhere in that 1.5 micron or the IR range, given the band gap is 0.6 or 0.7 electron volt. Okay, so no other material systems can give you such a wide spectrum. So that is why the gallium nitrides or III-Nitrides are so interesting. And not only that, the gallium, these are all interesting in terms of the optical or optoelectronic properties, but they do have these wonderful properties of the electronic as well. As you see, for example, if you look at the mobile communication, base station communications, all high power transistor, high power the communications. These are all the basic devices are made with the gallium nitride based heterostructures. So that I will briefly touch upon that because this is an optical, the seminar primarily focusing on optical properties of the material. So here is an example. So you can see here, by mixing these gallium nitrides, aluminum, gallium, and indium with the nitrogens, you can sort of get a light source varying all the way from deep UV to IR range. For example, it's only shown at 400 nanometer, but you can reach towards even the red and other regions as well. So that's the huge the benefits, and you can cover up everything in principles on one particular set of systems. So now where the challenge comes, right? So when, as I said, that when you grow a device, if we consider a device, it is not like one single structures or one single layer. So if, for example, I'll show you later on that if a simple LED structure will have a multiple layer of that. So first thing, we need to grow a layer on a substrate. Though one of the challenges that we see, unlike the 3-5 semiconductor, which is typically we understand gallium arsenide, is that we do not have a well-defined phase diagram. Why the phase diagram is very important? If you look at this gallium arsenide phase diagram, so the beauty or advantage of the gallium arsenide phase diagram is that if you look at the gallium, which is like, let's say on the left side, and the arsenic, both have the melting temperature, and even if the arsenic sublimes at 800, somewhere at 800 centigrade. So if you mix them together, you have a solid that has a melting temperature of 100 and 1238, for example. So all you have to do in this case is to bring gallium and arsenic in a 50-50 composition, which is a little bit challenging, but if you can make it, then you get a single crystals. In fact, that's the most favorite, the stable phase, for example. So that is not present, or that is not available for III-Nitride systems. One of the reason is that, the nitrogen we use quite often as an inert gas. That's because the nitrogen bonding are so stable and so strong. You break the nitrogen bond and eventually make a bond with gallium or group 3 elements is quite a bit challenging. So for any single crystal formations, what you usually do is you bring the system in an equilibrium situations, and then you go deviate the system in a little bit away from the equilibrium, you form the single crystals. Let's talk about the water systems, for example. So what is the sort of a temperature? 0 degree is this sort of a temperature that we talk about where 3 phases exist. Now, if you bring the temperature down to 0, for example, let's say minus 0.05, then what phase stable is that solid phase? It's solidify, and then that is because that's the temperature gradient, which is the driving force for the thermodynamic transformation of the liquid phase to the solid phase. And typically, this is what happens when a single crystal formations. Now, for III-Nitrides, you do not have this. You do not. There is no existence of such a phase diagram if we compare between the stability of nitrogens and gallium, for example. So all we have to do is to bring this, create a situation which is far away from thermodynamic equilibrium, and then you create a situations or a process condition that favors the formations of gallium and gallium nitride, for examples in this case. Now that is one challenge. So the formation of gallium nitride crystal. So because there is no gallium nitride crystal formation naturally, because there's no phase diagram as such, so you don't have a single crystal gallium nitride substrate. So if you want to grow the gallium arsenide based devices, you have a nice gallium arsenide substrate available in the market. You buy this gallium nitride substrate, and then you grow the multiple layer of the heterostructures that is required for your device. For example, LED photodetectors or whatever may be purpose. But in particular, this gallium nitride cases, gallium nitride materials, we do not have single crystal substrate available. Although recently there are some single crystal available, but not the large area single crystals, which is grown in differently. For example, it is not the typical single crystal growth technique. So we have to look for another substrate that is suitable for it. Now, I don't go into the details about the growth, but what the substrate that are available given these other the requirements for a layer grown on a single crystal substrate. We have sapphire, for example. So we have silicon carbide, we have silicons. Now, if you look at these, the heterostructures, the first thing we have, let's say single crystal substrate. Well, fine, we have available single crystal substrate, but let's look at the lattice constants. Like you are building the order systems, like here, for example, on the left side, you see there is a substrate, which is the single crystal substrate. Now on the top, you have a limitations. For example, you cannot grow a layer which has a sort of a lattice constant. Let's say lattice constant in the sense the distance between the two atoms in this case, far much different than the substrate. So that makes this, it's very challenging. No, so if you look at the mismatch between the lattices between the substrate available, sapphire, for example, or gallium, you have more than 30% lattice mismatch, which is hugely high, for example, in this case. Now, that is what it's making very challenging. Now, other things, if you look at its other substrate available, is the silicon carbide, and which is the most suitable substrate for gallium nitride. But one of the challenges with the silicon carbide is that the prices are super expensive. A 2-inch silicon carbide substrate costs $1,000, right? Whereas the sapphire 2-inch sapphire substrate costs $60, $50. So, for example, silicon, another way, silicon also has a large lattice mismatch. So these are the challenges we'll have to deal with, and that is why it took quite a long time, almost more than 2 decades, to come up with an useful device. Ever since the light emission was reported from this gallium nitride system. So it's become very challenging. So for example, here, now, despite having a very low lattice mismatch, even the silicon carbide, you see the 60 silicon carbide with aluminum nitride, gallium nitride, you have less than between somewhere 1 to 3% lattice mismatch. Now, despite having such a small lattice mismatch, the structure itself is a hugely defective, full of defect. That's because, as I said, thermodynamically, these materials needs to be grown in a situation which is far away from thermodynamic equilibrium. So you have very little control on the structure quality if you are not in the proper regime. So there are a lot of the extended defects which all the way comes from the interface to the surface, for example. So that makes the devices much less efficient in terms of the optical light emission, for example. So there are both challenges when you are looking at, let's say, gallium nitride based devices. Let's say when you are talking about the light emitting devices that require if we require an emissions in the range of 300 nanometer and below, so you'll have to make the aluminum incorporated into gallium nitride, and that makes things much more complicated and challenging. So today, that these aluminum nitride or aluminum gallium nitride based UV LED that are available, although if you can create a single crystals, you will have a very high bright UV LED. However, with this current technology or current quality of the layers, we can only achieve maybe maximum 20% light efficiency, for example. Okay, so those are the challenges when you grow. And then other things, if you look at, for example, we talk about the green gap. Now, the LED that you are using at home, for example, they are not the pure mixture of 3 primary colors. It is not red, green, and blue. So, however, your primary source or only source that you use for this UV or white LED bulb is this sort of blue LED or a little bit violet LEDs that are made with an indium gallium nitride with a little lower percentage of indium. So one of the reasons we have the green gap is that, as we have seen in the previous case, the aluminum incorporation was challenging. Here, the indium incorporation is also very challenging, because if you want to have a visible light, as I said, indium nitride has a band gap of 0.6 electron volt. Gallium nitride has 3.4 electron volt, which in turns gives you emissions in the range of 365 to 370 nanometer. So if you need a visible light, which is, let's say, 400 to 400 nanometer above, then you need to add the indium into it. So that's the beauty of this ternary systems. So if you have to achieve the green light, you have to have an indium of the order of 20% indium in order to get the emissions in the order of, let's say, 500 nanometer or 530 nanometer. So that is again more challenging. So the indium incorporations is again challenging because the indium and gallium has a very different thermodynamic properties. So as true for the aluminum and gallium as well. So these are basically the challenges the grower face to come up with a good quality crystal layer. Even with this defective layer, you see the efficiency has gone up, and you see a very efficient LED bulb today. So if you look at the watt per lumens, if you have, I mean, we can get even more than 200 lumen per watt. So that's the kind of the development has happened over the years. So there's a lot more potential, lot more room to improve if we just improve the structural quality. And now coming to the real sort of the device structure. Now, if you look at, this is an example of UV LED, but the essential, the LED structure, LED bulb that you buy, the primary emitter LED will have the similar structure. So you have a substrate, you have the base, aluminum nitrides. By the way, this aluminum, the substrate here we use particularly for LED is the sapphire, because that's a transparent and that will give you this the light emissions as well if you want to have the back emissions. So the aluminum nitride here plays a very, very important role. Usually, in fact, I will show you that this introductions of aluminum nitride led to the Nobel Prize at the end. So I'll talk about that story as well. So then it starts with this the first the strain management layer. You know, so as I see that the gallium the sapphire and the gallium nitride has more than around 30% lattice mismatch, you need the transition layer which would manage the strain. So because the active part, if you look at where actual light comes, is only this part. That's the active component where we have this indium, aluminum, gallium nitride multi-quantum well structure. All these accessories are necessary for the current injections. For example, N aluminum gallium nitride, N-type gallium nitride is required for the current injections, the electron injection particularly, and then on the top you have the hole injections on the top. So if you look at the, there are each of the layers or each of this sort of component that you see here has its own challenge. The first of all, you see, if you want to have a very high current injections, unlike the silicon, for example, you have, if you look at it, we don't talk about the contact. Here, getting a good ohmic contact is a big challenge. So there are many people, many researchers across the world, they're trying to sort of optimize, improve the contact. So to have the better injection of the current for an aluminum gallium nitride based layer, for example. And then, of course, because the doping, because of these materials are have large band gaps, so the doping also has a challenge. As such, the doping is not a challenge, but the carrier generation is very challenging because this dope or the dopant that you see or that are available, in order to activate the dopants, you need a very high energy. It is not the room temperature that will help us to activate those ones. So if you look at the numbers, for example, so for an N-type, it is okay. So if you dope the silicons, which is group 4, goes to the group 3 positions, aluminum or gallium positions, that requires an activation energy somewhere in 50 millielectron volt, 30 to 50 millielectron volt, which is much higher than the room temperature. So naturally, your doping or the carrier generation efficiency is much lower than when you're talking about low bandgap materials. The same is true with the hole as well. And in fact, this one of the challenges that needed to solve in order to come out with a high efficiency light was the whole a highly doped or an efficient doped P layer. p-GaN layer, for example. So that took almost more than 15 years to come up with an efficient techniques to have the good p-dop layer. So anyway, so I will just talk about some of these challenges and how the structural changes can help us mitigate those challenges. Okay, so you see here, many of you have seen this picture before, or we are right now the user of this technology. So the Professor Suji Nakamura, when he started his research as Nichia, the chemicals in Japan in early 80s, he had to go through a lot of struggle in order to come up with this proper technology. It took him almost like 10 years to, to grow a layer that are efficiently, primarily p-dop layer that would eventually was eventually necessary for growing or developing the high efficiency LED. So, but you see here, the first gallium nitride LED was sort of realized in the RCA lab in 1969, but this program was shut down in US in early 70s because of this very extremely low efficiency. So there were only a handful of scientists around the world that time. Primarily, there are very handful. So one of them is Suji Nakamura from, and in fact, Suji Nakamura came much later. But that time, you see here, there are primarily only one scientist who was still believing that this technology would work eventually, is this Isamu Akasaki. And his student, he's joined in early 80s to work on the gallium nitride, improving the quality of the gallium nitride layers on sapphire substrate. Now they came up with some of the technology. One of these, the technology was that process technology particularly was to introduce the aluminum nitride before growing the gallium nitride layer. Now there are two different ways to grow gallium nitride. One is that what we call the Nakamura techniques, because he sort of grow a low temperature grown gallium nitride followed by high temperature. However, this technique turned out to be much efficient, the technique that I'm talking about, which has the aluminum nitride in between. So it's eventually, if you look at the lecture, the Nobel lecture from Hiroshi Amano, was his students at that time. His talk starts with the impact of the aluminum nitride layer on the sapphire substrate to the quality of gallium nitride layer. So that was the first time the Nobel Prize was awarded for someone finding a process recipe to grow the gallium nitride. But the rest is history. As you see, we all are experiencing the inventions, and we all are benefited by these inventions. Now there's a lot of sort of revolution happened. Now, quickly to other side of this gallium nitride materials is that it's an unique, as I said. So all you have to do is to make a heterostructure, right? So for example, here, you see, if you make a heterostructure which comprises a gallium nitride layer, single crystalline, and then on the top you put aluminum mixed with the gallium, and then another thin layer of that. So if you look at the this part of the device, which is primarily the active part of the device, it consists of gallium nitride, then a very thin layer, which is like 1 nanometer aluminum nitride, which may not be necessary at this point, but then 25 nanometer of gallium nitrides. And what you get a beautiful device. This is very unique. You don't get any other materials. You don't have to dope anything. You get a transistor. So if you look at the band structures, because these are polar material, the structure is polar. So if you mix them, there is a gradient of electric field at the interface. This gradient of electric field will bring the charges at the interface, and these charges will be confined in a triangular potential well. And this is what we call the two-dimensional electron gas. You don't find any other material that would have such a properties, right? So you don't have to dope it. So the carriers coming from different places, for example, the surface state of gallium nitrides, the aluminum gallium nitrides, somewhere in the bulk, for example. So you just have to grow a nice crystalline layer. One is the gallium nitrides, and the another is the aluminum gallium nitrides. So that is something, is the heart of all these high power transistors, or especially for communication devices nowadays used. Okay, so now how we grow, let me just give you some of the brief descriptions of process. You see, as I said, the read, this is the read image that you get it during this molecular beam epitaxy growth. So as there is no substrate available, no single crystal gallium nitride available, we'll have to always look at the way or the process window that eventually help us to grow a two-dimensional layer. Large lattice mismatch is always very challenging. So that is why we need to look at very early stage of growth what is happening on the surface. As I said, this is the 2D layer, or the streaky read pattern is a signature of the 2D layer formations, and that immediately tells us, okay, we are in the right process conditions that is actually helping us to grow the two-dimensional layer. Apart from that, what is very important is that it is not the mixture of two materials. So as a source, we use the gallium and the nitrogen plasma, for examples. Now, this nitrogen and gallium are coming onto at the same time on the substrate. There's a reactions happening, for example, to form the crystals. Or so the interesting thing is that when you have the gallium atom coming on the substrate, we call them gallium adatoms, or nitrogen atom coming on the substrate, we call them nitrogen adatoms. Now, in order to form a two-dimensional crystal with sort of a best possible periodicity or ordering, this adatom need to move around on the surface in order to find their lowest energy positions, right? Now, it so happened that when the surface is sort of enriched with the gallium metal, for example, we use, if you look at the gallium nitride crystals, you have 1:1, 50% gallium, 50% nitrogens. Now, if you bring the 50% gallium and 50% nitrogen on the surface, then you may not actually be able to succeed growing the two-dimensional layer. So that's because the diffusion of the gallium adatoms, for example, on a nitrogen-rich surface, for example, much higher than if the surface is a gallium rich. That means if the surface is little metal rich. Now, how much metal you need? How much gallium lead? You need 1 to 2 monolayer of gallium. Now, how do you figure out it is 1 to 2 monolayer? We look at this read pattern or read intensity. See, if, for example, the moment you start this gallium nitride growth, you get the intensity drops because of the disordering on the surface. This is a specular beam. Again, remember that this is not the intensity that we are talking about. It's just the intensity of a specular beam, and which is here in this case. So it's giving the two things. One is that the ordering on the substrate, and another is the growth of the layer, for example. So you get this disorder, and then the intensity drops, and then if you just stop the shutter or stop the growth, you will see that it's regained after some time. Now, the time it takes to regain the intensity is that something that will tell us what the percentage or how many monolayer of gallium you have on the surface. So it's like an atomic layer precision that one has to follow in order to be able to grow this layer. So and the window of this process it's really narrow. For example, in terms of the substrate temperatures, we grow around 762, 765. It has to be 762 and 65. So that's the kind of narrow window. And this window, we fix it with the read. So it's very important to look at the read and understand this. Now, once you are able to grow the gallium nitride two-dimensional layers, and then you do all other characterization, for examples, the X-ray would give you the global structures and how the compositions and so on. And then these are all things which we eventually carry out. So, and that's quickly how you devise. This is like a typical device characteristics. We have these transistor properties, but you see when you are looking, I don't know how many of you are probably aware of these, the MOSFET, silicon MOSFET, we call these the inversion mode, because normally these MOSFETs are off, and then you apply the bias at the gate in order to switch on the channel, for example. Now, unlike these transistors, these gallium nitride based high electron mobility transistors, we call them, because this electrons really, the two-dimensional electron gas has a really high mobility. So the mobility of the order of in the range of 1500 to 200, for example, to 2000, for example. So whereas if you look at the bulk mobility of gallium nitride, bulk electron mobility, for example, or electron mobility in the bulk of gallium nitride crystals is somewhere between 400 to 600 centimeters electron volt second. Okay, so but if you make a two-dimensional layers, or if you make the able to generate the two-dimensional gas, and these electrons are confined at the interface, they don't go through the bulk of the semiconductor. If they have to go through the bulk of the semiconductor, they have to go through the electric field, periodic electric field, and which will have a phonon scattering and all other scattering. And so that is avoided, for example, and that is why these electrons, two-dimensional electron gas, able to sort of exhibit such a high mobility, and it is why it's called the high electron mobility transistors. And one of the challenges, one of the characteristic property is that these are primarily what we call the normally on transistor. So the transistor is always on because the 2-deck is present. Now you apply the bias at the gate, for example, and then to switch off the channels. So that is how it works. Anyway, that's quick. Now, if you look at the two-dimensional structures, all were okay, for examples, in terms of the transistor properties. But if you want to look at the optical properties, they are not so good, for examples. You see, one of the characteristic features that we see here, these are all the exciton-related transition. These are okay, but what are the disturbing fact that we see here, which we call the yellow luminescence? Now, if you look at the band gap, it's somewhere like the 3.2, 3.4, for example, or actual band gap 3.2, depending on the temperature you are measuring. But the emissions, that a broad emission that we see, which we call the yellow luminescence, is a characteristic feature of the defects, for example. So it attributes that your structure is a defective structure, and this defects could be extended defects, point defects. So there are a lot of things, and this still it is not very clear at this moment what sort of defects exactly present that would lead to such a yellow luminescence. So our aim is to basically kind of get rid of the yellow luminescence. One of the ways you will see in my presentation that we could shift the structure in a one-dimensional form, and this one-dimensional form will have no yellow luminescence. That means the structurally they are much more perfect. There are other advantages of having these nanowire or one-dimensional structures. Okay, now coming to this one-dimensional nanowire. So as I said, this is a unique advantage in an MBE system, especially for plasma-assisted molecular beam epitaxy systems. All we have to do is to play with the process parameter, change the 3:5 ratio, and then we can move from one set of one kind of structure to the another kind of structure. For examples, let me give you the schematic or the graph, for example, here on the right side. So here the gallium or nitrogen growth rate is 6 nanometer, and then just by varying the gallium growth rate, the gallium flux, for example, to be precise, you can move from, this is a compact layer, which is these two-dimensional layer formations, and then you have nanocrystals or nanowire, for examples, and then you have a no growth rate. Now you can see here, if you are basically at the low temperature regime, you can essentially have something like a semi-planar structure, and then these are all opening up. Eventually, by increasing the temperatures, you can come up with a one-dimensional nanowire structures. Now, the interesting thing is, if you look at their optical properties, so the growth, I'm not going to go into details, they are very sort of the unique or interesting or very useful in the sense. This is the room temperature photoluminescence properties, the measurements of a planar layer, gallium nitrides, and the nanowire that we have sort of seen in the previous one. So you see there's the yellow luminescence is not present here and it's missing. So that shows that there is a huge improvement in the structure by moving into the nanowire based heterostructure or nanowire based structures. All right, so now there was a challenging part at the beginning. I showed you, if you add the aluminum into gallium nitride, the structure becomes very defective. That can also be elevated or sort of circumvented by moving into the nanowire structure. Here is an example of the aluminum incorporation in gallium, 70%, 50%, 30%, and you see there is very uniform atomically sort of the distributed the aluminum nitride, aluminum gallium nitride nanowire grown on different substrate. Now, one of the advantages of nanowire is that you don't need a single crystal substrate as was needed for the planar structures. You can eventually grow this nanowire on any substrate, okay, because it's only confined within one particular regions, and then once you have the nucleation done, and then eventually the nanowire forms or continues to grow. So that's the advantage. You have to sort of, now this, once you have the nanowire based technology, you can grow whatever the heterostructure you want. Now, one of the things is that is a quantum well that we grow for the nanowire based LEDs. Here we have that you can see the aluminum nitride and gallium nitride superlattice, or in this case, this is a multi-quantum oil, and you can see that there is interface is atomically sharp. There is no defect present whatsoever, and also optically quite visible in this case. So that's the advantage once you have the best technology. Now, in the previous one, I showed you the aluminum, and here I'm talking about the indium gallium nitride. So as I said, we are working on the gallium the green LEDs and laser diodes. Here is an example of, you see the high indium incorporation, which in turn gives an emissions in the range of 500 to 600 nanometers with the same nanowire based indium gallium nitride structures. Okay, so and then now the final question comes: is the nanowire is a solutions? At this point, it is still very challenging, because when you are talking about commercial viability, it is far below than the planar structure, because your efficiency, light emission, overall light is still significantly lower than the planar structures. So people are working on it, we are working on it, so hopefully we'll have some solution in near future. Now, there are other benefits of the nanowire. Is that one of the benefits is to basically have the defect free that we saw. There is a fundamental study showing that your critical thickness between the two layers become very high. So if you just move your radius, for example, or that means you shrink your radius. Okay, so that's one of the advantages you can get it here. And so there's another big challenge is that the doping. So if you look at the large band gap, which is aluminum nitride, so the dopant level far away from the band edges, if you look at it. So the doping energy or the activation energy is super high. So this is a planar structure I'm talking about. Now, if you move to the nanowire, you can see at the surfaces of the nanowire, this one corresponds to the surface, and the doping activation energy reduces significantly. That's a first principle study which shows this magnesium doping in aluminum nitride significantly reduce in terms of the activation energy. So that's also beneficial. And then some of the recent results also shows that it could eventually grow or sort of make the very deep UV. This is 207 nanometer light emitter using this aluminum gallium nitride based structures. Okay, so there are a lot of results, a lot of experimental recent progress have been reported, and also the new reports coming with a better efficiency and the better they'll sort of the device structure. Okay, now so where are the limitation? As I said, so only limitation at this point is the output power, because when you are trying to make a device which is commercially viable, so we need to talk about the overall light output, and it is still far below the planar heterostructures or planar layers. So hopefully this will be solved soon. Now, coming to my last part quickly, I will just move into this because the time is running out. So this I'm not going to describe. Now, here is this another very interesting thing I'm going to talk about. As I said, we are working on the room temperature operating the single photon source. Here, the single photon source is the photon source which emits the light. I think you understand better than me. Emits the one photon at a time. Now, what is the criteria? You have to have real quantum dot, for example, is one way. Now, so that there's this significant confinement happening, energy levels are far separated, and then you can get the single photon source. Now, one of the advantages of III-Nitride system is that the band offset between the two different composition can be very high. So you can literally produce a quantum well with a very large barrier, and then in that case, you literally can create some sort of structure. So one way, as I said, we adopt our nanowire based technology in this way, and I'm going to show you how we did. So the challenges was that if you have a, let's say this is a barrier, which is the aluminum nitride 6.2 electron volt, and in between if you want to put the gallium nitride, which is 3.4 electron volt, and then it is encapsulated by aluminum nitrides. So it's essentially a quantum well structure. But this, if you look at our quantum dot, they claim, if you look at the structure, it is not typically quantum dot. It's sort of an island structure. That's because the gallium nitride weights the gallium aluminum nitride. So it's quite difficult to produce a real quantum dot. So what we adopted is the technology is that so we try to use this nanowire as the template, and then we convert this nanowire as a quantum wire, and then those quantum wire actually are holding our sort of a template to sort of place those quantum dots. You will see here in the structure, these are the gallium nitride nanowire, and we sort of produce this, convert this gallium nitride nanowire into the quantum wire, and then these quantum wire are the sort of a template for holding those the structure. For example, here in the tiny tip you see here, this is where our quantum dots are placed. And if you look at high resolution the transmission electron microscopy, here you see the gallium nitride quantum dot placed on the nanowire, on a nanowire template, a gallium nitride template, for example. Now, this is a typical 3D confined structure. If you look at, this is the X, this horizontal directions is 5 nanometer, almost less than 5 nanometer, which is far below or below the confinement range or excitonic Bohr radius for gallium nitrides, and vertically you can control. So this way, we could sort of create a nanostructures or a quantum dot that eventually give us these very strong confinement, and that we eventually showed here. You can see ultimately we are looking for generating the single photon source, and G2 correlations is one of the ways to look at the photon correlations, and we see some of our nanostructures or quantum dots placed on a gallium nitride nanowires truly shows the strong G2 correlations at room temperatures. And finally, you will see that if you look at the cathodoluminescence of those nanowires coming from it, although these are all, this is just the green as a representation. It is not a green tube because this is emitting 3 UV light with an energy of 3.65 electron volt. And these are primarily confined only at the tip of this nanowire, you can see here. So that's, by doing that, you are kind of ensuring that those quantum dots are truly confined in all 3 different directions, and then only you are able to see the correlations at even room temperature. No other system would show correlation, G2 correlation at room temperature, except only challenge here is to sort of put the gallium nitride quantum dot or indium gallium nitride quantum dot if you are working on a visible range at this range. So with that, I think it's too heavy at this point, so I'm just going to end. And I'll be happy to take the questions. So I just want to thank you for sort of your time, and I'm looking forward to sort of get some of your feedback or any suggestions or any clarifications if you want to.